So in this problem, we are given a binary tree and our task is to find the maximum path sum, right? So now a path is a sequence of nodes connected via parent-child edges, right? And it can start and end at any node in the tree and must include at least one node. Also, it is not necessary that the maximum path always passes through the root, right? So for example, in this tree, if you see, the path 15, 20, 7 actually gives the maximum sum, right? Which is 42, and it doesn't pass through the root, right? So that's the entire problem statement. Now maybe you can just pause this video and try to think of a solution. And once you're done, you can just come back and check the solution here. Okay, so now to solve this, we will define a recursive function basically inside our main function to do post-order traversal, right? That means we will process a node only after processing its left and the right subtrees, right? And we call this recursive function from within our main function on the root of the input binary tree, right? So now in this recursive function, for each node, we will compute two values. The first one is the path price at the current node, which is essentially the sum if we start a new path that passes through both the children and the current node itself, right? And the second value that we need to compute is the maximum gain passed to the parent, right? And that will be the best one path sum we can take upward from the current node towards its parent, right? And why do we need these separate values? Because see, the maximum gain passed to the parent must be a single path. We can't actually go both left and right if we are extending the parent's path, right? But the path's price at the current node will allow both children, right? Since we can start a brand new path over here. Also, we will just ignore the negative gains from the left or the right child because including them would only reduce the overall path sum, right? Instead, we will just treat negative paths as 0 to effectively cut them off, right? And this way we are always building optimal paths, avoiding any negative branches, right? So let's see a step-by-step traversal of this particular algorithm on a sample tree. So over here, if you see, we begin our traversal at the root of the tree, which is node -10. And currently, if you see, our maximum path sum is initialized to -infinity as we haven't visited any node yet, right? Now, since we are using a post-order traversal over here, we will first explore its left subtree. So from node -10, we move to the left child, which is node 9. Now this is a leaf node, meaning it has no children, right? So now we compute the path sum at this node. And since node 9 has no children, both left and right gains are 0, right? So the path sum through node 9 is simply 9 itself. And this becomes our current maximum now that we have seen so far, right? Now we return 9 to the parent, which is -10, because that's also the best single path value that can be extended upward, right? Now back at node -10, we have finished processing the left child, and so now we can move to the right child, which is node 20, and begin processing it recursively. Now from node 20, we go to the left, that is child 15. Again, it's a leaf node with no children, so node 15 also contributes 15 itself, as both left and right gains are 0 for it, right? So the path sum at node 15 is also 15, which is greater than our current global maximum, so we update it to 15 now. And also we return 15 itself to node 20 as the maximum single branch gain from this path, right? Now we visit node 7, which is the right child of 20. And like previous leaves, node 7 also has a gain of 7 itself with no children, right? And the path sum at this node is 7, and we return this value to the parent node, which is 20, right? Now we are back at node 20 over here. We received gains 15 from the left and 7 from the right. So the total path sum through node 20 is 15 plus 20 plus 7, which is equal to 42. And this is our maximum path that we have seen so far. And so we just update the global maximum to 42 now, right? But we just can't return the whole 42 if you see to the parent -10, right? Because a path passed upward must always be linear, as we have been discussing, right? So we return the maximum single side gain to the parent, which will be 20, which is the current node's value, plus maximum between 15 and 7, right? And that will lead to 35. So this is the best one-sided path we can extend upward, right? So at this step, I think it should be very clear to you now that why we can't simply pass the maximum current sum at a given node directly to the parent, right? Now we are back at root, which is -10, right? The left gain is 9 from node 9 and the right gain is 35 from node 20, right? So the total path through minus 10 will be 9 plus minus 10 plus 35, which will be equal to 34. And since 34 is less than our current maximum of 42, we do not update the global maximum, right? And now finally, we return one child's gain from this final recursive call, which will be equal to minus 10 plus maximum between 9 and 35, and that will be overall equal to 25, right? But this return value, if you see, will be sort of useless as there is nothing upward of minus 10, as minus 10 is the root, right? And we have already calculated our maximum path sum, which is stored in the global max path sum variable, right? Which we will simply return as the result. So that's the entire step-by-step traversal of this particular algorithm. Now maybe let's quickly recap the key concepts over here. So first of all, why do we compute two values at every node, right? One is the price of the full path through the current node used to update the global maximum, and the other is the maximum gain we pass to the parent, right? Since the parent can only continue one path, right? And also, why do we ignore the negative gains? Well, that's because a negative path will only reduce the total sum. So we discard any child path if its gain is negative. So that's the entire solution. Now maybe let's see the code for this implementation. So we start by defining the structure of a tree node, which represents a single element in our binary tree, right? So the constructor first of all takes the value val as the input and initializes the node, right? So we just assign the input value to self.val and initialize the left and the right child pointers to none, right? And this is a standard setup for any binary tree node, right? Now we define the solution class that will contain our logic to compute the maximum path sum, right? Now this is where we define the main function called with the root of the binary tree, right? And it returns the maximum path sum for the entire tree, right? Now in this function, we first of all initialize a global maximum sum to negative infinity so that any path sum we calculate will be larger to begin with, right? And this variable will keep track of the best path sum that we have seen during the recursion, right? Now we define a helper function, maxGain, which calculates the maximum gain starting from the given node, right? And this will be a recursive post-order function that we have been talking about, right? So firstly, in this particular function, our base case would be that if the current node is none, we simply return a gain of 0, since no value can be really contributed from a non-existent node, right? Otherwise, we recursively compute the maximum gain from the left and the right subtrees. And if the gain is negative at any point, we just discard it, right? Because negative paths would decrease our total value. And this is the crucial optimization that we have to keep in our mind, right? Now we compute the price of a new path that passes through this particular node, right? Including both left and right children. And this is a local path and may become our global maximum as well, right? And now we just update our global maximum if this local path sum is actually greater than anything that we have seen before, right? And this will ensure that we consider all the path shapes and not just the one that is going straight down, right? Now this is the value that we actually return to the parent node, right? The best one-sided path. Why? Because a parent can again only extend one child, not both, to avoid forming a cycle, right? And then finally, we begin the recursion with the root node by calling the maxGain function like this and return the final result as the maximum path sum found in the entire tree from the global max sum variable, right? So that's the entire solution implementation. Now let's talk about the time and space complexity for this solution. So the time complexity of this would be order of n, where n is the number of nodes in the binary tree. And that's because we are visiting each node exactly once during the post-order traversal, right? And for every node, we are performing a constant amount of work. That is, we are computing the left and the right gains, calculating a path sum, and possibly updating the global maximum, right? That's all what we are doing at every node. And there are no repeated computations or nested loops at each node, right? And that's why the time complexity over here will be order of n, right? And now talking about the space complexity, it will be order of h, where h is the height of the binary tree, and this is the space used by the system's recursion stack during the traversal, right? And in the worst case, if the tree is skewed at one side, height will become equal to n, which will lead to order of n space, right? But in a balanced binary tree, the height is always log n, so the space complexity is better, order of log n over here. So that's the entire solution. I hope you understood it well, and now I will see you in the next problem. Happy coding.